Hello everyone, welcome to Neso Academy. Till now we have studied arithmetic operators, logical operators and relational operators. And today we are going to study something very interesting, shift operators. This concept is extremely important in digital electronics because processors and digital circuits continuously shift data internally. So, in this lecture we will understand what are shift operators. Now, let's start the lecture. We all know what are operators, and in VHDL there are 6 operators, out of which we have completed arithmetic operators, logical operators, and relational operators. And in this lecture, we will understand different types of shift operators. Now, what are shift operators? Shift operators are used to move bits left or right inside a vector. That is, shift operators are used to move bits left or right inside a vector or multi-bit signals. In simple words, shift operators move binary bits either to the left or to the right inside a vector. And shifting changes the bit positions of a signal or vector. That is, shift operation changes the bit positions of a signal or vector. During a shift operation, the bits inside the vector move from their original positions to new positions. And in VHDL, there are 6 shift operators. First one, shift left logical operator represented by SLL keyword. Second, shift right logical operator represented by SRL keyword. Third, shift left arithmetic operator SLA keyword. Fourth, shift right arithmetic operator SRA keyword. Fifth, rotate left operator ROL keyword. And the last, rotate right operator ROR keyword. In this lecture, we will understand each of them. Let's start with shift left logical operator. The first shift operator, shift left logical operator, that is SLL operator. Now, shift left logical operator moves all bits toward the left. That is, SLL operator moves all bits toward the left side. Every bit inside the vector move to the left side. And leftmost bits are discarded and 0 enters from the right side. When bits shift to the left side, the leftmost bits goes outside the vector range. That is, leftmost bits are discarded and 0 enters from the right side. As bits shift to the left, an empty space is created on the right position, and to fill that empty position, we use 0, and this 0 is called as 0 padding. Let's understand this SLL operation using an example. For that, I am taking a signal. Example, signal A as standard logic vector 7 down to 0, meaning signal A as an 8-bit standard logic vector as 101101110. Now, I want to perform shift left logical operation on this signal A. And after performing the operation, I want to store the result. For that, I am creating another signal Y with same data type and same length. Now, I want to shift the signal A to the left side by one place. For that, I will write A SLL 1, meaning shift left logical signal A by one place and store the result inside the signal Y. Now, we all know A is equal to 101101110. Now, as per this operation, I want to shift this vector to the left side by one place, which means this leftmost bit, the MSB, will be discarded and the rest of the bits will move to the left side by one place, which will create an empty position on the right side, and 0 will fill that empty position. So, vector will move to the left by one place and this MSB will be discarded and empty position is filled with 0. So, the output will be 0, 1, 1, 0, 1, 1, 0, 0. This 0 comes here, this 1 comes here, and similarly, the rest of the bits will move to the left by one place. Now, in the same way, I can shift this vector by two places. For that, I will write A SLL 2, and the vector A will move to the left by two places, which means these two leftmost bits will be discarded and the entire vector will move to the left by two places, which will create two empty positions on the right, and we use zeros to fill those positions. Therefore, these two leftmost bits will be discarded and zeros will be added on the right side. Output will be 110, 110, 0, 0. So I hope you understand how to perform shift left logical operation. Now let's see second operator. Shift right logical operator, that is SRL operator. Shift right logical operator moves all bits toward the right. Now, shift right logical operator is similar to SLL operator but in opposite direction, which means every bit inside the vector move to the right side and the rightmost bits are discarded and 0 enters from the left side. When bits shift to the right side, the rightmost bits are discarded, which will create the empty position on the left side, and zeros are used to fill those empty positions. Now let's understand this using the same signal A. Signal A with this value. Now I want to perform SRL operation on this signal A, and after performing the operation, I want to store the result. For that, I am taking another signal Y with same data type and same length. Now, I want to shift this signal to the right by one place. For that, I will write A SRL 1, means shift right logical signal A by one place and store the result inside this signal Y. Now, I want to shift this vector to the right by one place, which means this rightmost bit, the LSB, will be discarded and the entire vector will shift to the right by one place, which will create an empty position on the left side, and 0 will be used to fill that empty position. So, shift the vector to the right by one place. Therefore, this LSB will be discarded and the entire vector will shift to the right by one place, which will create an empty position. And the output will be 0, 1, 0, 1, 1, 0, 1, 1. In the same way, I can shift this vector to the right by two places. For that, I will write A SRL 2. And this vector A will shift to the right by two places by eliminating these two rightmost bits and adding two zeros in the left side. So the output will be 0, 0, 1, 0, 1, 1, 0, 1. So this is shift right logical operation. Now let's see third shift operator, which is shift left arithmetic operator, that is SLA operator. Now, shift arithmetic operator and shift logical operator are same, but shift arithmetic operator always try to preserve the sign of a number. Now, we all know what are signed numbers. Signed numbers include both positive and negative numbers. But in binary values, how to identify the sign of a number? Using the MSB. MSB of a binary value act as a sign bit. Let's understand this first. MSB of a binary value act as a sign bit. If MSB is 0, then the number is positive. If MSB is 1, then the number is negative. Let's take an example. For that, I am taking 5-bit binary value. Here, MSB is 0, which means this number is positive. In this case, MSB is 1, which means this number is negative. So overall, MSB will act as a sign bit and the remaining bits will represent the magnitude of a number. So 0 means positive number and remaining bits 0, 1, 1, 1 represents number 7. Overall, positive 7. In the same way, 1 represents negative number and remaining bits 0, 1, 1, 1 represents number 7. Overall, 1, 0, 1, 1, 1 represents negative 7. So I hope you understand how to identify the sign of a binary value. Now back to SLA operator. SLA operator moves all bits toward the left. Every bit inside this vector move to the left side, and it is similar to logical left shift. That is, shift left arithmetic operator is exactly similar to shift left logical operator. But SLA operator does not guarantee sign preservation, meaning in SLA operation, it is not necessary that the sign of a number will be same. Let's understand this using an example. Consider the same signal A. Now I want to shift this vector to the left by 1 bit using SLA operator. Now SLA operation is exactly similar to logical left shift. Now here the MSB is 1, which means this number is negative. Now let's perform the SLA operation. Shift the vector to the left by 1 place, remove this MSB and add extra 0 on the right side. Now the output will be 0, 1, 1, 0, 1, 1, 0, 0. Now in this case, the MSB is 0, which means now this number is positive. So here sign changes. But let's shift this vector to the left by 2 places and see what happens. For that I will write a SLA 2. Now shift this vector to the left by 2 places, which means remove these 2 leftmost bits and add zeros on the rightmost empty positions. The output will be 110110000. In this case, the MSB remains 1, means sign does not change. So I hope you understand that shift left arithmetic operator does not guarantee sign preservation. Now let's understand the fourth one, shift right arithmetic operator. SRA operator. SRA operator moves bits toward the right while preserving the sign bit, which means every bit inside the vector move to the right side, but SRA operator preserves the sign bit. In SRA operation, the sign of a number does not change. So, MSB is copied repeatedly and the sign remains unchanged. To keep the sign same, MSB is copied repeatedly. Now let's make it more clear with an example. Consider the same signal A. Now in this case, I will shift the vector to the right by 1 place. Now the rightmost bit LSB will be removed. But here, instead of adding 0 on the leftmost empty position, I will add the MSB value, meaning I will add 1 in the empty position. So, shift the vector to the right, remove the LSB and add 1 on the left side. So, the output will be 1, 1, 0, 1, 1, 0, 1, 1. Now, in this case, the MSB remains same, means the sign of a number remain same, even if I shift this vector by 2 places. For that, I will write a SRA2. So, the vector A, shift to the right by 2 places, which means remove these 2 rightmost bits and this time fill the empty positions using MSB. So, the output will be 11101101. So, in these cases, the MSB remains same, which means the sign remains same. So, I hope you understand that in SRA operation, sign remains unchanged. Now, let's understand the fifth shift operator, which is rotate left operator, that is ROL operator. Now, in rotate left operation, bits shifted out from the left and re-enter from the right side, which means every bit inside the vector move to the left. And instead of discarding the leftmost bit, we will use those bits to fill the empty position on the right side. Therefore, those bits are used to re-enter from the right side. Let's understand this using an example. Same signal A. Now, let's rotate this vector by 2 places. Let's break it down bit by bit. So, first shift this vector to the left by 1 place, which means this MSB will be removed and re-enter from the right side. Shift the vector to the left, so this MSB will move to the right side and the output will look like 0 1 1 0 1 1 0 1. Now move the another bit, means the second bit. So shift the vector to the left side by one place, which means this MSB will move to the right side. So shift the vector to the left and this MSB will go back to the right side. So the final output will be 1 1 0 1 1 0 1 0. So I hope you understand how to perform ROL operation. Now what should be our next operator? Obviously, rotate right operator, that is ROR operator. In ROR operation, bits shifted out from the right re-enter from the left side. Now ROR operation is exactly similar to ROL operation, but it is in opposite direction. So every bit move to the right side and the discarded bit from the right side will re-enter from the left side. Let's take the same example. Here A is 10110110. Now I want to shift or rotate this vector to the right by two places. So this 0 on the right side will re-enter to the left, then this one on the right side will re-enter from the left. So the final output will be 10101101. So this is rotate right operation, and I hope you understand all 6 shift operators, as shift operators efficiently help us manipulate binary value and are extremely useful in digital electronics. So we are done with this topic of shift operators, which means we are done with this lecture. I will see you in the next one. Thank you.